Now, this video is completely optional, but if you would actually like to learn how to use Apache Beam, I would recommend watching this before getting into the nitty-gritty of test questions. So, if you're ready, let's begin. Your Beam driver program typically starts by constructing a pipeline object, and then using that object as the basis for creating the pipeline's datasets as P collections and its operations as transforms. To use Beam, your driver typically must create an instance of the Beam SDK class pipeline, typically in the main function. When you create your pipeline, you'll also need to set some configuration options. You can set your pipeline's configuration options in the command line, but it's often easier to set the options ahead of time and pass them to the pipeline object when you create the object. If you look here, here's an example of the format that you should use when creating a pipeline object. You're going to import Beam, and you're also going to say with beam.pipeline as pipeline, and then you're going to construct your pipeline after that. So this is the format that we're going to be using every time. Beam SDKs include a command line parser that you can use to set fields and pipeline options using command line arguments to add your own custom options in addition to the standard pipeline options. The following example shows how to add input and output custom options. Let's take a look inside the code. First, we've imported the Apache beam.options.pipeline_options. This interprets the command line arguments that follow the format with the option name and the value. I'm not going to say the exact format, you can look at it. Next, we've defined our own class, myOptions, and passed in the imported Apache Beam class. For Python, you can also simply parse your custom options with argparse. Now your pipeline can accept input equals value and output equals value as command line arguments. Let's talk about creating a P collection. After you've created your pipeline, you'll need to begin by creating at least one P collection in some form. The P collection you create serves as the input for the first operation in your pipeline. You create a P collection by either reading data from an external source using Beam's source API. This is typically how a production pipeline would ingest data. Beam's source APIs contain adapters to help you read from external sources like large cloud-based files, databases, or subscription services. And we'll actually get into this later in our sources and sinks section. Or you can create a P collection of data stored in an in-memory collection class in your driver program. This is primarily useful for testing and debugging purposes. The following example code shows how to create a P collection from an in-memory list. To create a P collection from an in-memory list, you use the Beam provided create transform. This transform is applied directly to the pipeline object itself. In this example, lines. Inside the create transform function, we pass in a list. In this particular example, we pass in a list of Shakespearean lines from Hamlet as strings. Here we have characteristics of a P collection, and I've broken down the different characteristics of a P collection. So the data types can be any data type, but a P collection, they all have to be the same data type. So if you have different data types, you need different P collections. Apache Beam SDK includes built-in encoding for common data types. There is also support for custom encoding. P collections do not support random access for individual elements within the P collection. Transforms are applied to every element within the P collection individually. Okay, now P collections are immutable. That's important. So whenever you perform a transform, that P collection is not going to get eaten up. It still exists. So once a P collection is created, elements can't be added into it or removed. Beam transforms do not change P collections. They use the elements from the input P collection to create the output elements. They do not change the elements of the input P collections. So that actually is pretty important, that even though you're changing, you're actually changing a copy of it and not the thing itself. To invoke a transform, you must apply it to the input P collection. Each transform in the Beam SDKs has a generic apply method or pipe operator. Because Beam uses a generic apply method for P collections, you can both chain your transforms in a sequence, or you can apply the transforms that contain other transforms nested within. Now, this is called composite transforms in Beam. How you apply your pipeline's transforms determines the structure of your pipeline. Now here we have an example of what applying 3 transformations to the same P collection would look like with both the code and a graphic representation. But note that a transform does not consume or otherwise alter the input collection. Remember that it's immutable. Now, part do is a part of the core Beam transforms, and I have a whole other video that's just devoted to core Beam transformation. So if I talk about a transformation before describing it, it's because I have a whole nother video on it. So here is how you would apply 2 different Pardue transformations on the same input P collection. So all you really need to know from here is how you can perform two different transformations on the same P collection. You can also build your own composite transforms, which is the nested transforms, that nest multiple transforms inside a single larger transform. Composite transforms are particularly useful for building a reusable sequence of simple steps that get used in a lot of different places. We're going to talk about map transform. Now, this is technically the second transform that we're actually going to go into detail on. The first was create, and that was to create a P collection. Now, map transform accepts a function that returns a single element for every input element in the P collection. This function can include additional arguments to map. The function passed to beam.map can be inbuilt functions or user defined. Now we're going to get into the nitty gritty of user defined functions as well. That's part of the core Beam transforms. So anytime you need exactly one output element returned for every input element in your P collection, use beam.map. And this is why it's often used with print to output the results. Map can be thought of as a special case of Pardue. Map is expected to produce exactly one output for each input, while Pardue can emit 0, 1, or multiple elements to an output P collection. In this example, we've defined our function, strip header and new line, that accepts one argument. We're applying the inbuilt strip function to our element and passing in the additional argument to strip the element of any pound signs, blank spaces, and new lines. The arrow points to what the resulting output would be. The flat map transform applies a simple one-to-many mapping function over each element in the collection. The many elements are flattened into the resulting collection. In simpler terms, it maps a P collection of n number of elements into n number of collections of 0 or more elements, which are then flattened into a single P collection. This should be contrasted from the map transform, which maps from a P collection of n elements into another P collection of n elements. So the regular map is a 1-to-1 ratio. Now the flat map is not necessarily. In this example, we've defined a user function that returns the Python string split method, which splits a string into a list of strings after breaking the given string by a specified separator. And in this case, it's a comma. Next, we start our pipeline. We've named our output P collection plants and our input P collection gardening plants. Now, this list may look exactly like our previous example, however, it's not. In our previous example, we started a string and then we had a pound sign and then the icon and then the name of the fruit and then the new line command and then finally a comma before we had the next one of the same format. In this example, our first string has strawberry, carrot, and eggplant with their icons, making this a collection instead of individual elements. Though the resulting output is the same, our P collection is in a different format, therefore requiring a different transformation. Filter accepts a function that keeps elements that return true and filters out the remaining elements. In this example, we define a function isPerennial, which returns true if the element's duration equals isPerennial and false otherwise. Then we create a pipeline with a P collection of produce with their icon, name, and duration. Finally, we pass our function directly into the filter transform. Please be aware that we never use function parentheses when passing our function to the transforms unless that function has arguments. Now, as we can see over on the right hand side, that's going to be our output of this filter transform. This example code is exactly the same as the last one, except for this time we do not start off defining a function. We passed in a lambda function to the filter transform instead. If you're familiar with lambda functions, they are anonymous functions. In this case, this function takes the single argument plant and returns the same output as the previous example with just less code that's required from the user. Well, that's going to wrap this video up. We've covered some basic Beam concepts, such as how to create a pipeline object, how to create a P collection with the create transform, how to apply transformations or P transforms on P collections using the map transform, the flat map transform, and the filter transform. We've also showed two different ways of using the filter transform, but just know there are 6 different ways that you can use the filter transform, but that's beyond the scope of this video. I'll see you next time.